Hello, my name is Toby Buckley. I'm a PhD student in Dr. Ed Colgate's lab, working on developing autonomous controllers for humanoid robotics. This is my CE495 final project. In robotics, we generally want a system where inputs are fed into a controller or algorithm and intelligent commands are outputs, which can then be executed on the robot hardware. Usually, the inputs consist of observations in the form of images and state information, and the output commands are either joint position or joint torque commands. This is our dexterity nexus, or DexNex. It is a humanoid testbed for hardware, software, controls, and algorithms. I developed the platform for the Hand Engineering Research Center. Ultimately, we want to develop autonomous controllers for this real robotic system. In the meantime, though, it's beneficial to experiment in simulation. DexNex was recreated in MIT's Drake simulator, a high-fidelity simulator for contact-rich simulations. The tasks we're interested in often require dexterous manipulation, where upwards of 66 joints are controlled simultaneously. Many algorithms suffer from the curse of dimensionality, so special care must be taken when working with such large action spaces. Simulation allows us to test theories in safe and fast environments before applying them to the costly and slow real hardware. There are three popular techniques for producing robot controllers. The first is hand-coded controllers. These work best for low-level controls, but don't scale well to high-level problems like manipulation. Next is behavior cloning. Most modern humanoids use this to do manipulation. The issue is that it requires more expensive human time, and your controller will only be as good as the datasets. Last is reinforcement learning, the focus of this project. RL is usually slower to train and churns through much more data, making it only suitable for simulation. Let's take a moment to review different methods for numerical optimization. There are zeroth order methods, like guess and check or the cross-entropy method, which do not require any gradients to work. Instead, they directly compare the objective function value for different inputs and update the input according to some algorithm. Next are first-order methods. This category includes gradient descent. Gradient descent uses the gradient of the objective function with respect to the inputs to determine an optimal direction to move the input values in. If the dataset is too large to compute the optimal direction for all data points, then stochastic gradient descent is used instead. Let's skip to second-order methods, which includes Newton's method. In this, the Hessian of the objective function with respect to the inputs is calculated, and that is used to determine the optimal step size for the update rule. Last, there are quasi-second-order methods. Computing the Hessian can be very slow and require much more memory, so an approximation can be computed instead. Let's review stochastic gradient descent. It works by computing an average gradient from a batch of samples, sampled from a dataset, and then moving in that gradient's direction with some fixed step size. This process is repeated for some period of time, or until convergence is reached. Finally, let's review LBFGS. It is a quasi-second-order optimization method which approximates the Hessian using the value of the gradient from previous calculations. Graphically, it's like fitting a quadratic equation to some objective function landscape by using the information from multiple linear lines. Let's also briefly review neural ODEs. They work by training a network to approximate an ODE. It's trained on the MSE loss between its output and the true derivative value from the ODE. The objective of this project was to compare the performance of some different techniques for robotic action generation. For this project, a simplified robot and task was defined. A single finger is locked to planar motion and is tasked with rotating a puck counterclockwise. The finger has 3 controllable joints. Each episode is locked to 5 seconds with a time step of 0.1 seconds. And the reward for each step is how many radians the puck was rotated counterclockwise since the last step. For the comparison, several baselines were first tested. They were PPO, TRPO, and SAC. The details of these algorithms are out of the scope of this project. The first test trained a critic identically to soft actor critic. The only difference was that the actor was never trained. Instead, during inference, an action was initialized from Gaussian white noise, and then an online optimizer, either Torch's LBFGS or SGD, was used to produce actions. The algorithm used the gradients of the critic with respect to the inputted action to modify the action until convergence was reached. Two variants were tested, one using LBFGS as the optimizer, and one using SGD. The second test was a neural ODE trained on the gradients of the prior tests, the actorless soft actor critic's critic. During inference, instead of having to do a forward and backward pass with the critic, only the forward pass of the neural ODE was needed. In theory, this should decrease inference time required. For this, only LBFGS was used as the optimizer. The third test involved using PPO, but defining its output as the gradient of the action instead of the action itself. An online optimizer can then use those gradients to generate high-quality actions to be executed on the robot. To train this, a subproblem was defined in the iteration space. The PPO algorithm existed solely in this iteration space, and instead of rewards coming from the true task environments, they came from a task critic, which was trained on the true task rollouts. The PPO's reward was simply how much better the task critic liked the new proposed action compared to the old action. This was computed from the difference in Q values. Let's see the results. The three baselines are seen in magenta, blue, and teal. TRPO does best, followed by PPO, and then SAC. Test 1, using LBFGS and SGD, is seen in yellow and red, respectively. Test 2 is seen in green. And lastly, Test 3 is seen in purple. The biggest thing to note is that with SAC, using the critic's gradient with LBFGS to produce actions greatly outperformed all the other variants. The gradient version of PPO also exhibited a much better learning curve, but unfortunately crashed in performance shortly afterwards. I believe that this is due to a bug in my software, however, so I remain very optimistic about this method. Here, we can compare the inference statistics for the different techniques. PPO had both the fewest number of parameters, as well as the lowest inference time. TRPO had the greatest reward, but took twice as long for inference. Each of the iterative approaches was much slower in inference, as expected, but only the SAC critic gradient LBFGS outperformed the baseline SAC and peak mean episodic reward. Surprisingly, the SAC neural ODE was slower during inference and performed roughly equivalently to the baseline SAC. Perhaps there is a bug in my code which caused this. Lastly, with significantly fewer training steps, the PPO gradient LBFGS was able to reach half the mean reward of the baseline PPO, albeit with a slower inference time. I plan to investigate the gradient version of PPO in more detail to identify what's causing the reduction in performance. That's my project. Thank you.